Good? Yeah?
Yeah, hi everyone. Welcome to ML Monday. Today we're going to be continuing the part 2 of advanced reinforcement learning. So there's a QR code to sign in, answer a few phone questions, I'll do. And okay, now I've lost focus, I think.
Oh, sorry. My bad. I was changing something. No, you should be good.
Sweet. Okay, so yeah, today we're going to be talking about advanced methods. So first thing we're going to talk about is a review of last time. Then we're going to move on to deep Q-learning, which is just going to be using Q-learning except with neural networks. Then we're going to be doing a little demo of a deep Q-learning simulation with OpenAI Gym. We're going to talk about policy gradients. And finally, we're going to talk about recent advancements, which are going to be trust-based, region policy optimization and proximal policy optimization, which we'll see. Okay, so a review of what we did last time. We essentially tabulated an optimal solution to every state action pair of an environment. So if you remember, for every state, there's an optimal action we can take. And so we have like a Q value, which assigns the quality score of that state action pair. And if we're at a given state, we just pick the highest value in the row, and that action corresponding to that value is going to be the action we take in the optimal policy. And so that was tabulated Q-learning. And recall that we had focus on.
Oh, my bad.
Okay.
Sorry.
There we go. So recall that we had a couple of issues. The first is that tabulated Q-learning only works for discrete state and action spaces. So if I want to output an action that is like 2.5 or 7.3, that's not going to work because we can't like bin that, or we can bin that into actions. But by default, we're not going to have a way of saying like this is action 0, action 1, action 2, etc. And so if we were to like change it to discrete action spaces, we would need to like bin them. For example, like instead of having like 0.3, we would just say like, oh, like between like 0, 1, 2, 3, etc. Like some sort of finite discrete values that we would have to assign. The other problem is the curse of dimensionality, which tells us that if we have a very large number of dimensions, the Q table will be infeasibly large. So if we wanted to tabulate the solutions to Atari Breakout, for example, the number of pixels on the screen is going to be 255, the shades of a grayscale color. To the power of the screen size, the resolution is only 300 by 200, but this is already more than the number of atoms in the universe. So it can never fit in memory. To solve this, we're going to use a function approximator. And this function approximator is going to be a neural network, a deep Q network. Focus again?
Oh, yeah, you're good.
Oh, okay. So to review this, we're actually going to look at a research paper. And this was published in 2013 by DeepMind. DeepMind is a subsidiary of Alphabet. It's like a sister company to Google, essentially. So it was originally acquired by Google, but after a little restructuring, Alphabet is the parent company of Google, and Alphabet is also the parent company of DeepMind. They work a little bit independently. DeepMind's like in Britain, London, I think. They do a lot of like great research with machine learning and reinforcement learning in particular. So yeah, the paper's name is Playing Atari with Deep Reinforcement Learning. You can scroll down a little bit to the abstract. So essentially what they're saying is this is a convolutional neural network trained with a variant of Q-learn. So that's going to be that Bellman equation that we discussed last time. And so what they do is they play on 7 Atari games, and we see that it outperforms all previous approaches on 6 of the games and surpasses a human expert, meaning gets superhuman performance on 3 of them. So pretty good paper. Let's scroll down a little bit to the introduction. So basically what it's explaining is the Q-learning environment, the Markov decision process we were discussing last time. So here, we can scroll down a little bit, yeah, a little more. So those are some screenshots from some games. And scroll down some more. It's mostly in the background. Yeah, so you see that we have this A, which is a set of actions from 1 through K. So K is just the number of actions we have. An image X, they call an X instead of like O or T, O or S, but this is essentially the state with observation. It's really the observation that we get from the screen. So X is nothing but all the pixels on the screen at that given time. It's going to be a matrix of the grayscale values of the pixels. And so that's coming from the emulator. And we're going to receive a reward R of t, so a reward at each time step representing like how good our action was essentially. And we have the current screen x of t. And here's one interesting thing. We have the state t is equal to actually a sequence of states and actions. And the reason for this is from a single Atari like screen, you cannot see like the velocity of the ball. So if you just have a still picture of the ball and the bar, you can't tell in what direction the ball is going. You actually need several frames in order to do that, to see that movement. And so the observation itself is not sufficient as a form of information to like solve the problem. We need to concatenate several frames in order to get a description of motion. And that's why we're doing x1, a1, x2, all the way through at minus 1, xt. So they're going to use a Markov decision process. Recall that a Markov decision process is a set of states, a set of actions, a reward function, and some other things like a discount factor, a horizon, etc. Horizon is just the number of time steps that the experiment will run for. So they define a cumulative reward function as the set of a given time step t as the sum of discounted rewards of the individual time steps. And t is the time step at which the game terminates, so t is the end time step. We define this optimal action value function, q of SA, and our goal is to maximize the expected reward. This capital R is the cumulative reward, as defined up here. So given the current state, the current action, and the policy, we want to maximize the expected value of cumulative reward.
Okay.
Yeah, scroll down. And yeah, up there, this is the Bellman equation. So explicitly states that it's the Bellman equation. We're going to use an iterative update. We're going to assign nothing but the current reward at the time step plus a discount factor times the maximum Q value that assumes that we take the optimal action in all future cases. And so this is a recursive formulation in which we can optimize the Q value. Now we define a loss function. So in neural networks, the primary objective is to formulate some kind of loss function that we can then minimize. So a loss function tells us how bad the model is. And if you have a function that you want to minimize, recall from calculus that this is nothing but where the derivative is 0. So if the derivative at a point is 0, it's either like a local minimum or a local maximum, right? And specifically in deep learning, instead of directly computing an equation in which like the derivative is 0, this turns out to be like just computationally infeasible. Instead, what we do is we start at some random point and we move the point by the gradient. So raise your hand if you've taken calculus 3. Okay, so all of you know what the gradient is. Great. The gradient is the direction of steepest ascent, right? If you want to minimize a loss function, then you want to go exactly the other way, the direction of steepest descent. So you have a loss function if you have at a given point on a function, right? You want to move in the direction of steepest descent. If you want to maximize the function, you want to move in the direction of steepest ascent. So it's going to be either the negative gradient or the gradient, respectively. And so the loss function tells us, it quantifies how bad our prediction is. And if we can minimize a loss function, then we will get an optimal policy. And so what this is this is the expected value of the state and action sampled from the probability distribution of the target Q value that we want, subtracted by the current Q value of the state, action, and given theta. So theta is the parameters of the model. It's the weights and biases. These are parameters that the network is going to learn. I'll talk more explicitly about this a little later. But essentially, we're going to take this subtraction and we're going to square it. And the reason is, if we subtract two numbers, we could either have a positive or a negative value. But if we square the result, it'll always be a positive value. It always tells us exactly how bad, like the magnitude of how bad it is. And the other nice property of it is that it's very easy to take a derivative, because what's the derivative with respect to x of x squared? It's nothing but 2x. So we get a very simple derivative, a very simple gradient from this loss function. And they also state that y of I is the expected value of this Bellman equation. Does anyone have any questions to this point? Great. So this is mostly a review of last time. We just formulated a loss function for the neural network instead of using a tabular model. Let's go down a little bit. Yeah, so to derive the gradient, scroll down a little more, scroll down. Yeah, all right, so now we get to section 4, deep reinforcement learning. And so this is where we use a deep neural network instead of a Q table. And this is going to outperform the Q table by quite a bit. And so essentially we're going to use stochastic gradient descent. We're going to introduce a new method called experience replay. And so experience replay is the idea that we have some sort of memory. So every time we take an action, what we have is we have a state, we take an action, we get a next state, and we get a reward. So these 4 values form a vector, and we can store all of these vectors across time in a matrix. This is like a history matrix. We call it the replay table or the replay buffer. And afterwards, in future time steps, we can sample uniformly from this, this matrix. So what that means is that we can learn from past experiences. Just as like humans can think back on memories and learn from their mistakes from a long time ago, the replay buffer gives the machine learning model a way to sample from past experiences and optimize the policy based on those past experiences. So it's nothing but a concatenation of previous experiences in that vector form. It's a matrix. So they define E of t as the vector of the current state, action, reward, and next state. So these 4 values make up a single experience. If you concatenate all of these experiences over time, you get the replay buffer. Yeah, replay memory. And then it says we can sample E. This tilde just means sample. It means like take a random row of that matrix out of the distribution. Scroll down a little. Yes, okay, so this is like the full algorithm, right? And it's also not terribly long. It's only a little bit longer than the tabular key-learning method, actually. So we first start by initializing replay memory with nothing. We just have a capacity, n. So that's the number of rows in that replay table. So what that means is that we have like n rows for experiences. If we ever pass n, it's going to be like a queue. We're just going to drop like previous rows. So we're going to initialize the action value function q with random weights because we don't have any idea what q is. We can all we can do is give random guesses for the weights of q. And for episode 1 through m, what we're going to do is first we're going to initialize a sequence s1. So the reason for this is that recall that x1 is only an observation. It's a single frame. And from a single frame, we don't have a concept of motion. We can only see a still image. In order to see what any movement is in the image, where the ball is moving, where the paddle is moving, we need to concatenate observations into multiple frames, which will give us a state, s1. So that's why s1 starts at x1. We're going to append later on. And we're going to have a preprocessed sequence. Don't worry too much about this. They're just going to preprocess the sequence using some arbitrary function phi of the state. So from time step 1 through t, so recall that t is when the simulation ends. So until the simulation ends, this is like a single episode. We're first going to run that epsilon greedy algorithm. So with probability epsilon, we're going to select a random action a of t. Otherwise, we're going to select the greedy action, the action that maximizes our q value. So we're going to take a of t is the maximum a of the q value of that preprocessed state, the action, given the parameters data. So this semicolon, all it does is it denotes like a barrier between the direct function arguments and the parameters. So theta is the parameters of the neural network. S and A are actual like parameters to the function itself. So those are inputs to the function. We're going to execute the action a of t in the emulator, and we're going to observe the reward r of t in the image x t plus 1. So we put in x of t, or we have x of t, the emulator is in state x of t, and by taking action a t, we get a new state xt, or a new observation xt plus 1. Then we're going to set the state xt plus 1 is equal to the current state, the current action, and the next frame xt plus 1. We're going to preprocess that. We're going to store this transition. This is just the experience. So we're going to store the phi, the action, the reward, and the next state in the replay memory D. We're going to sample random mini batches of transitions, rows from D. So a mini batch is just going to be like a small number of randomly selected rows in that matrix. We're going to set y, the target value, either to the reward if the state is terminal. So if the state is terminal, that means we can't like progress any further. So we either died or we won. We can't take another action, and therefore the only reward we can assume is the reward, the immediate reward. Otherwise, if it's non-terminal, that means we can continue to take actions. So we take the immediate reward and add the discounted future like maximum sum rewards. So this is the Bellman equation that we discussed last time, the recursive formulation of the immediate reward plus discounted sum of future rewards if the state is non-terminal. And finally, we're going to perform gradient descent. So this is where you start at some point on the function, and you're going to try to minimize it by walking down the function. So you're going to find the direction of steepest descent, and you're going to move a little bit in that direction and continually find the gradient and move down to the function as much as you can. And so the function that we're trying to minimize is the loss function y of j minus the q value squared, according to equation 3. And that's the entire algorithm. Deep Q learning with experience replay. This method outperforms 6 models on Atari, 6 like of the best models of the time, and outperformed the best humans at 3 of them. Any questions on this algorithm? Yes?
So when you do gradient descent on the loss function there, what are you updating? Are you updating like the
Theta.
y?
The only, when you are doing gradient descent, the only thing you are updating is theta. Because theta is what the neural network uses in order to compute the outputs. Any other questions? Yes?
According to the loss function, why do we want the square? Why do we want to minimize the square?
Okay, so let's say that there's no square. Let's say that y of j is 3 and that q is 1. The loss is 2, right? Now what if y of j is 1 and q is 3? Then the loss is negative 2. But the difference between them is exactly the same, right? They're 2 apart. We don't want to have this concept of positive and negative. How bad it is, how far away it is always 2 in that case. Does that make sense? So if you square it, it'll always become positive.
Well, why don't you use the absolute value?
Great question. Why don't you use the absolute value? So this actually is a term called like mean absolute error, and something you can like read up on. The main reason is that the absolute value is like the square root, all right, of it's like all the terms squared, and like it's like the square root of this term, right? Is the absolute value.
So it's just redundant?
So the reason is either works. However, it's easier to take the derivative of a function squared. Like it's easier to take the derivative of like x squared than the absolute value of x. Because when you have like when you're trying to take the derivative of the absolute value of x, now you need to do like a piecewise segmentation, right? Of like what is the slope. And when you compound that over many, many functions, it becomes very, very difficult to do.
So you say it's difficult not only for humans, but in terms of like time efficiencies as well?
So I'm not necessarily sure about time efficiencies, but essentially just like constructing that like piecewise function is going to be a lot less nice than this. And another reason is because any point at a like sharp corner is non-differentiable. So for example, if you have an absolute value function, then what is the derivative at the point like x equals 0, y equals 0? Well, like there is no derivative, right? It's not differentiable at that point. Here we have a smooth function. Like if you have x squared, it's differentiable at every point. Does that make sense?
Yeah.
Yeah, so great question. Basically, this is easier to take a derivative of. Another reason is that it penalizes like bad errors more because of the square. So the square really punishes like bad results. So for example, if you have like y is 3 and q is 1, then the difference is 2 and the square is 4. So if they're 2 apart, then the square is 4. The badness, the loss function has a value of 4. But let's say they're like 3 apart. 3 apart is only a little bit more than 2 apart, right? It's only 1 more. But 3 squared is 9. So that's actually double how bad the previous one is. So it really starts to penalize the model when its predictions are far away. So it really penalizes bad mistakes and rewards like very precise estimates. Does that make sense?
That makes sense.
So yeah, good question. A number of reasons why we use the square as far as the gradient is concerned.
But wouldn't you have those same penalties and rewards, really penalties for mistakes and rewards for precision, even more so if we raised it to the 4 power?
Yeah, it would. I guess you could do that. You could experiment with how it works. But so far, people have been using squared for a long time, and I think it performs the best out of any of these kind of experimented loss functions so far.
There's also another reason that, like, if you have considered all the possible things that you can represent given the parameters, using the square regression will force it to converge to like the mean of the distribution. Per se.
Oh, okay. So yeah, there's a statistical reason as well. Yeah, yeah, good question. A lot of different reasons why we use square. It's been very effective. Yes.
I'm not sure if it's super related, but like with the simple statistics classes where you have the sample deviation with they take the square root of the sample variance as well. So that's what you do here too.
Yeah, you could. It's kind of like, yeah, this is more like variance than standard deviation, right?
Yeah.
I think, yeah, oftentimes, I think statistics is like a different kind of exploration of these things. It's kind of tangentially related, right? But yeah, it's like variance. Standard deviation is defined in terms of variance and not the other way around. Yeah. Great. We can scroll down a little bit. Let's see if there's anything else. Okay, so let's see model architectures. I don't think there's too much important information here. Scroll down a little bit more. They have a table. Yeah, okay. So this is kind of nice. This just shows you the performance of their model over time. So this is the number of training epochs. Epoch is just like one iteration of like the entire batch. So it's going to like, it's essentially like one iteration of the model that we take gradient descent on. And this is average reward per episode. So in any given episode, what is the reward? And you can see that this line is going essentially like up and to the right, which is exactly what we want to see. As the model trains, we want to see it get better and better. You can see that there's some noise. It's not a perfect line. It jumps up and down quite a bit, especially if you consider like at about epoch 50. It's like all the way up here. This is the maximum point it has in the 100 epochs. Even though in theory, the longer it trains, it should be better, the better it should be. There's a little bit of noise which causes like it to have a very low reward on, for example, epoch 62. This is just a normal thing that you'll see. Same here, this one is even more extreme. On epoch 80, the reward is actually extremely low. Like, it looks like low, like double digits. So it's on breakout, this on sequest, but essentially, a couple of them, the Q values move up and to the right very smoothly. So the Q values, remember, are something that our model predicts. And the reward is something that like the environment actually gives us. So the Q is like an estimate, and the reward is like the tangible reward that the environment provides. Okay. Yeah, they use epsilon greedy with epsilon equals 0.05 for 10,000 steps. One epoch corresponds to 5,000 mini-batch weight updates and roughly 30 minutes of training time. Scroll down a little bit.
Yep.
Yeah. Okay, so that's a little game. Yeah, different frame numbers, Q values, initialized value. I don't think any of these are particularly important.
I think that was about it. This table maybe?
Yeah, this table just compares some different like algorithms, including human baseline.
I think that's so funny.
Yeah, on these games. So I think it said like it beats a human in 3 of them. Let's see. So it seems like wins on breakout more than humans do. Seems to work in Pong.
And Doro.
Oh, and Doro, yeah. Yeah, okay, so it outperforms humans on 3 of them, and outperforms all their models on 6 of them. So this paper was published in 2013. At the time, this was a very novel argument. But as we've seen, it actually just takes the Q-table formulation and applies it to neural networks. So all of our like Markov decision process discussion and Bellman update concerns like all apply to this neural network. Okay, let's try on a little bit. I think this is about it though. Yeah, conclusion, we introduced a new deep learning method for reinforcement learning, demonstrated its ability to master difficult control policies for Atari using just the pixels. So this is quite cool because as a human, you only have access to the pixels also, and that machine is also taking in those same pixels and generating an output from it. And
all right.
yeah,
So
that's the end of the paper.
yeah.
Yeah, I think so that's it. Oh yeah, I guess we have a little demo. So I think we can pull up the demo and the code at the same time.
Yeah.
So I wrote a small deep queue network on OpenAI Gym's cart poll. So this environment is just a poll on a cart, and the AI is able to, like the agent is permitted to move the cart in order to balance the poll. We don't want the poll to fall over. If the poll hits a certain degree, the game is terminated.
So you just clone the repo, and then you can just do Python main.py, and then run this.
Yeah, so at first it performs extremely poorly, but over time it learns the Q values and converges. So I think we can look at the code while it's running, and at some point it will start to converge.
Sorry, what's the goal of the game?
The goal is to get it to balance as long as possible.
Oh, okay.
Yeah, it's actually quite hard to balance. Even in like a human scenario, this is quite difficult. Like if you were to take one of those markers and try to balance it on your palm, it's quite it's quite a difficult thing to do.
Well, isn't that compounded by the fact that your palm is compelled to move even
Yeah.
in a minute amount? Whereas
Yeah, so there are biological
the
reasons
cart
too.
does not have the same impulse.
Right. There are biological reasons too, but like if once like the object's in motion, you need to perform some kind of action to stabilize it, and that stabilization is quite difficult to perform because you might, if you don't like move your hand fast enough, then it'll fall over this way, and if you move your hand too fast, it'll fall over the other way. So it's actually quite hard to get that right balance, that like precision that you want in order to control the marker. Okay, so yeah, scroll up a little bit. Yeah, so.
Oh yeah,
Right.
that's
Yeah, perfect. Okay, so we import some modules. We're gonna
Ignore the green stuff.
oh right, so yeah, Ka added.
I added some
just
stuff so it looks better on the
metrics.
stream.
Yeah, nice. Yeah, so basically we're going to define a Python class QLearner and then .module. This is a PyTorch thing. Whenever you want to declare a model in PyTorch, you just subclass this nn.module. We'll talk more about this in Intro to TensorFlow and PyTorch. We're going to initialize it with an input size. These are default parameters. So like the input size is 4, meaning like there will be 4 values in the vector that that's the input of the neural network. The output size is 2, meaning there will be 2 values in the vector that is the output of the neural network. There's the epsilon, which is just our epsilon in the epsilon greedy algorithm. We have a train start. That's like, the idea is that we don't start training until we've collected 1,000 samples to put into the replay memory. And so the train start means that is the iteration on which we start actually training the network, sampling from that replay buffer. We're going to set the hyperparameters, so you can see the epsilon decay is 0.998, so we're using exponential decay for epsilon. And we're setting a gamma, that's going to be our discount factor. And here are our layers. So it's actually quite easy to define a simple like neural network in PyTorch. All you do is you call this nn.sequential wrapper, which basically says like you're going to do this, then this. It's a top-down approach where you start from the top and work your way down to the bottom in terms of layers. So the first is a linear layer. This is a very standard neural network layer. This is just a fully connected layer. I can explain this a little more if we have time later, but this is like a general machine learning neural network principle. We have a ReLU. This is an activation function. This is also some foundational machine learning theory, and we're just going to repeat that essentially until we get to our final output layer. We're just going to have the output size number of values in the output in that vector. Our forward function is going to tell it how to compute like the output. So if you think about it, you start from the input and apply this forward function to get the output. And this is just like the layers of x. So we define layers up there. If you just call like nn.sequential, if you call that function, it'll give you, on the like input x, it'll give you the output y that you desire. We have this function act. It's going to act on a given observation and iteration. And so all we're doing here is we're saying if the iteration is more than train start, so if we've started training, it's past that 1,000 iteration mark, then we're going to train, right? So we're going to use that epsilon greedy algorithm. So, or this is not epsilon greedy, this is just changing the epsilon according to exponential decay. So we multiply by the decay. If it's less than 0.1, we'll just round it down to 0. Otherwise, we'll return a random value from, I think, okay, let's see. Oh, this is just taking a random action. Because this is the act function, we're just taking a random action if the random value is less than epsilon. Otherwise, can we scroll to the right horizontally?
Yes.
So torch.argmax is just going to take like the action. Argmax means like take the action rather than the value, but like take the action of the output at which like the Q value is highest. So like there's two outputs. Whichever one is higher, take that one, is what argmax means. And we're going to take the tensor of the observation. So the observation, we're going to wrap it around the PyTorch tensor, and we're going to return like the output that has the output value that has the highest value, and that's what the dot item means. It means like unwrap the tensor, give us like the actual value instead of the tensor. Okay, go back. And in our learning, all we're doing is we're sampling from this. So this record is just some kind of packed like tuple in Python, and we're going to unpack it a little bit. If it's terminated, then we don't want to be terminated, so we'll set like a manual reward of -100 to penalize the model. Prediction is going to be just run the model itself on the tensor of the observation. So we always need to wrap the observation around the tensor for PyTorch to understand that it's an input. And then finally, we're going to get the next value. So V is for value. We're going to take the maximum of like the model itself on the next observation, and we're going to torch.clone is just going to take this prediction tensor, and it's just going to make a deep clone, meaning that like if we ever modify prediction, it's not going to affect the value of y. This is a concept of mutability in programming languages. Like if you have like x equals some class and you do like y equals x, then if you change x, that will change y in turn. But if we do this clone, then they'll be completely separate. Finally, we we set the y of the action that we're taking to the reward if it's terminated. Otherwise, the reward plus the discounted value function, so like the sum of future rewards. That's that line in the paper. We compute the loss as a loss function of the prediction of y. And we zero the gradients. This is all like PyTorch stuff. We'll talk about this more in Intro to TensorFlow and PyTorch. But essentially, like when you have a loss function, you don't actually have to like do calculus to compute the gradient by hand. Instead, you just tell PyTorch what the loss function you want it is, and it'll automatically differentiate that function for you in order to converge the optimum that you want. Okay, so this is the replay buffer. It's actually pretty simple. Dec is a Python data structure. It means double-ended queue. And the max length is 2,000. We're going to train start. And essentially, all we're doing is we're just appending like the sequence of like the state, action, next state, reward, and whether or not it's terminated to the replay buffer when we want to. And if we sample, we're just going to take a random sample of that with the batch size. So if the batch size is 64, that means that from that replay buffer, we're going to take 64 of those rows randomly. And that is going to be our sample. And the length is just the length of the table. The environment is going to be the environment created by OpenAI Gym. We're going to render it as human. QLearner, we define this class. Now, our loss function is MSE loss. This means mean squared error. So what we define in the paper is the squared error, and we're just going to average that across all samples. And finally, this atom thing is just a way to essentially go down that function in a very fast manner. So we will talk more about optimizers as well in Shota, TensorFlow, and PyTorch. There's learning rate, there's replay buffer, and we're just going to run for the number of episodes. And as long as it's not done, we're going to increase the score because what we're trying to maximize is like the time at which the number of time steps the model can go without falling over. And we're just going to run through all of our actions that we want. Yeah. That is the algorithm. Any questions about the algorithm? Yes.
So how you compute the y?
How do we compute y? Okay, so let's go on.
It was expectation is just one single reward.
This one?
No, I mean
Y. So y is
from this code corresponds to the yi in the paper.
Mm-hmm. So this y is for like the y that's not I is going to stay unchanged. The y that is I is going to be such the reward if it's terminated. Otherwise, reward plus the discounted some future rewards, as in the paper.
And reward is what is one game.
So the reward is whatever the environment gives back to us. I think in this case it'll be 1 because like as long as it's going, it'll it'll increase in reward. Essentially, you want to like maximize the amount of time that it stays up. So I think reward will be 1 in every episode, or else like it'll be constant in general unless it like falls over.
also.
Oh, yes. So you saw initially it was like falling over all the time. Now it's doing a little better. By the way, if it hits like the edge of the game, then it dies. So now it's learned to like balance to some degree. It's learned through the neural network, essentially in what direction to move in order to survive a longer period of time.
Yeah, and you can see the moving averages here.
Yeah. So after 71 episodes, we're at a moving average of 179.
That's a 10 moving average.
Oh, yeah, 10 episode moving average. Yeah, that makes sense.
Okay.
Any questions? Yes.
Once you have like I guess a set of parameters that work really well for the neural network, where do you go from there? Like after
So,
training the model?
yeah, you just lock those parameters, you save them to a file, and then whenever you want to use the model, instead of training anything again, you just use those parameters. You can just load them up, and you don't have to train anything. It'll be very fast because you can just like run those, those saved parameters.
And if it can be improved, like you would just have you could train it from those parameters.
Yes, you can. So you can. The parameters are nothing but like a bunch of numbers, like these matrices. And if you store them in a file, then if you recover the file, like if you load from the file, then you just inject it into memory essentially, and you can train starting from that point instead of like starting from scratch. Great. Yes.
I assume the network will also learn to like overcompensate when it's near the edge, so it doesn't.
It should, yeah. Ideally, it should. I'm not sure if it'll do that because the number of episodes it's been moving at is relatively low. But in theory, it should try to stay towards the center.
Yeah, I'm gonna run it the entire time, so at the end we can look at it.
Yeah. Great.
Alright.
I think that's it for Q-learning. We can move on to policy gradients.
Alright. Oh, wait, that's on this. Hold on. I'm trying to find it now. There it is.
Okay. And I think like before we start on policy gradients, I think I want to flesh out a little bit of what I was explaining with Q networks. Like, what is a neural network, right? Raise your hand if you're like already familiar with neural networks. Okay, so actually like half of us are, so that's good. A quick introduction for like anybody who isn't is like if you think about it from a very high level, a neural network is what we call a function approximator. It takes in an input and gives you an output. It's trying to approximate some kind of function. So what I mean by that is that let's say you have an input, and let's call this like a vector with m entries. So let's call this vector x, is typically what we want. And we want to map it to some kind of output y. And these are not necessarily the same length. So this, we can say is n entries, right? So let's say like, in this case, m is 4, and n is 2. So what we really wanted here is we wanted like some like vector of like, let's say it's just 4, 1. This gives you like some, in that environment, it gives you some kind of physics quantities. Like I think like momentum or velocity or numbers like that. And we just want to like tell it how far we should move in the left or right like directions, or actually like whether we should move right or whether we should move left, essentially. So if we, the reason is like if we want to move left, then that will correspond to this index here. If we want to move right, it'll correspond to this index here. So like this might be like this will be the Q value in this case of what we want. So like let's say moving left will kill us, then the Q value might be like -1, right? It won't be perfect, so let's say like 1.2. And the Q value moving right might be really good, so like let's say 0.6. And then we will take the right value because it's higher than the left value. That's what we mean by the argmax. Does that make sense? So the argmax of this is the index at which it occurs, which is 1. So this index is 1. It's not equal to the max. The max is 0.6. But the argmax is 1 because it's the index at which 0.6 occurs. That's the action that we want to take. So a neural network is nothing but a means to map an input vector to an output vector. What we're talking about in data is the parameters of the neural network. So the idea is that, let's take a simple example. What happens if we have some kind of matrix theta 1 when multiplied by x? And this gives us y. Let's say that our model is we take a matrix theta 1 multiplied by x and get y. So if the matrix theta 1 is correct, we'll actually have like a pretty good approximation for y, because we're essentially mapping using this matrix from this vector to this vector. Now, if the matrix is wrong, if it's like random values, for example, it won't do so well because it's not going to like fit that model of mapping x to y. So our goal of training a machine learning model is to optimize the parameters theta such that they do create an accurate mapping between the vectors. Does that make sense? So like, yeah, a neural network will typically involve many matrix operations. So it might be something like, let's say like theta 1 times x. And you're also going to add this thing called a bias term. This is like a y-intercept. So if you have like a graph like this is going to be in the form y equals mx plus b. So this m is equivalent to theta 1. This b is equivalent to theta 2. Except m is now a matrix instead of a scalar, and b is also a vector instead of scalar. So this is just a multivariable formulation of a line. Does that make sense? Okay. And in a neural network, you're just going to take this and do it multiple times. So the output of this, you can multiply by another matrix theta 3, add theta 4, so on and so forth until you get to y. And you also have activation functions, things like that. Yeah.
Well, I was going to ask, is theta 3 an activation function or just a scalar?
Theta 3 right now is just going to be a matrix, but you can do like, you know,
Sigmoid?
yeah, activation function, whatever you want. But that's kind of going out of scope here because our focus is on reinforcement learning rather than neural networks in particular. We will talk about neural networks in more detail in future ML Mondays. So in this case, the idea is we can map any general vectors to other vectors. In this case, we're actually not mapping a vector, we're mapping a matrix for the Atari game. Although in Cartpole, we are mapping a vector of 4 values to a vector of 2 values. And these 2 values are the q values of, essentially, it's going to be, the first value is the q value of moving left. This is an approximation. And the other one is the q value of moving right. And it's easy to see that the action we're going to take is the one that is larger. Does that make sense? So we're just training a neural network to estimate the q value of each output, given the input of the state. Cool. So that's Q learning. I'm going to talk about policy gradients. Policy gradients are the idea that we can actually differentiate our policy directly. So up until now, we've defined this Q value, we've defined a formulation in which we can optimize this proxy measure that tells us like the quality of being in the state and action at a given time. But what if we can just differentiate the policy directly and apply calculus in order to arrive at an optimal policy? So that's what we do with policy gradients. This is a very long or like very involved mathematical derivation. So please make sure to ask any questions like immediately whenever you think of them. Yes?
So would this be more applicable to like continuous states?
Exactly. This is one benefit of policy gradients. Instead of like Q tables where like we have to work with like discrete states and actions, we can work for any continuous state action pair because like we can work with any like continuous quantity that we want to estimate because we're directly differentiating a continuous function. Great. So what we want is we want a policy pi of theta. So theta is going to be the parameters of our neural network that predicts an action given a state t. So what this means is that pi is going to tell us the conditional probability of taking action a of t given the state s of t. And so this will be some value between 1 and 0 because any probability is between 1 and 0. It doesn't make sense to say that like your probability of winning a coin flip is like 1.5 or -3. Like it doesn't make sense. All probabilities have to be between 1 and 0. And so in this way, we can define our policy in a continuous manner. So how can we take the derivative? So our goal is to formulate a utility function, u of theta. So theta is our parameters of the neural network. We want to change these to ones that will be optimal. U is just telling us how good our model is, utility, how good it is. And the way we're going to define this is just the sum across all state action sequences of the probability of that sequence delineated by the hyperparameters. So if you change your hyperparameters, I mean not hyperparameters, if you change your parameters, then you'll take different actions due to different policy. Therefore, it'll give you a different probability of encountering states and actions, multiplied by the reward. So I'm using this abbreviation tau here. What tau means is the first state, we're going to call it S naught, first action, next state, next action, so on and so forth, until the, like let's say, T state in action. So this capital T is just the length of the game. So that's what I wish to point.
Is it a tuple?
What?
So is it essentially a tuple?
It's a very long vector, potentially. Yeah. So let's, is that clear?
Yeah.
What T means? T is just the sequence of like states and actions.
What is U?
U is the utility function. It's a function that tells us how good our model is. It's a function that we want to maximize.
Alright.
Yes.
Wait, so you said the probability function is like given a certain data, given the parameters, it's the chance of encountering.
Exactly. So let's say that we have a Markov chain like this. So let's say like this is state A. And so we have like, let's say a 0.3 chance of going back to A and a 0.7 chance of going to state B. And then we have like a 0.5 chance of going to state C. And here we have a 0.3 chance of going back to B and a 0.2 chance of going back to C. So what is the probability of this, of like, let's say tau, when tau is equal to A, then B, then C? 0.35, right? Reason being, in order to get to C, we have to get to B. In order to get to B, we have to start at A. We're assuming A is the start state. That's not. Is that clear to everyone? If we start at A, in order to get to B, we have to take this probability like 0.7. In order to get to C, we have to expend this probability 0.5. And so the probability of this tau, given that our like walk length is 2, is going to be 0.35. You can multiply these probabilities in order to get a probability in C. Now you can also like go to B, go back to A, go to B, go to C. But if we constrain like the walk length to 2, our probability is 0.35. So that's what this tau means. This tau is just a shorthand way of writing like any kind of sequence of states that you traverse. Yes?
But if tau is continuous, would this not end up being an integral as opposed to just a sum?
If tau is continuous.
Yeah, like a continuous set of states and or actions.
Right. I think in a continuous case, yeah, you would have like an integral instead of a sum, but the same like principal logic applies. Yeah. So here we've defined this utility function. What this means is this is the expected value of the reward. So this here might seem a little confusing, but essentially we're weighting across all possible paths the probability of that path given parameters theta. So all we're doing is we're weighting based on the probability of something happening, the reward that it gains. So it's like of a coin flip, or like let's say of a dice roll. If you win like $6 when you roll 6, and you lose $1 otherwise, then you have to multiply the probability of winning a 6, which is 1/6, by the reward, and add it to the probability of not winning a 6, which is 5/6, of losing $1, so -1, and you get like some expected value, and that's going to be like so this like sum times p, sum of p. This is nothing but expected value of the reward. So these symbols don't really need to be closed. Now what we're going to do is we're going to take the gradient. Because remember, if we can take the gradient, then we can maximize its function. We can do it analytically by setting the gradient equal to 0. That's going to tell us where our local minima and maxima are. We can find the maxima. all of this is computationally infeasible, so we can just like take that function and move it in the direction that we want. So in a little illustration of what I mean by that is like, let's say you have some kind of, let's make it 3-dimensional, but it'll be many-dimensional in a machine learning model. You can extend to whatever number of dimensions you want. Let's say we have some kind of function that starts here. Okay, so it's some kind of like concave up function. And we start, like this is the minimum point. Let's say we aren't able to solve this analytically. What we can do is we can start at this position, and we can find the gradient. The gradient is going to tell us the direction this way. And so then we like guess, let's move a little bit closer, a little bit closer, a little bit closer. And so each step is going to be that gradient of the, like let's say the function is j, theta. In this case, theta is going to be the x and y axes, and j is going to be like that.
Shouldn't that be the negative gradient?
Oh yeah, you're exactly right. Yeah, this is negative gradient. Gradient tells us to do the direction of steepest ascent. This is the direction of steepest descent. Good catch.
And if j is a Jacobian?
No, j is just some function. I can call it like f if you want.
Oh yeah.
Yes.
Are there any cases where in this summation above, like, you don't necessarily want like a linear relationship between like the reward and the set, like the actions you took? So let's say like, I'm trying to think of like an instance, like you really, when you fall into the water, like you really never want to do that.
Mm-hmm.
Is there maybe like some function that you would?
So reward is like, reward can be negative, right? So if you have a sequence of actions that leads you to like falling into the water, the environment should give you back a reward like -1 or something like that.
Okay, so you would change that inside the reward function.
Yes.
Not
Yes, that would be exactly like constrained within the reward function.
Okay.
Great. Okay. So the gradient of u if you take in linear algebra, you know that the gradient operator is a linear function, meaning we can push it inside of the summation. If you haven't, it's still a simple concept. It's just the idea that if you take a derivative of like a sum of values, it's equal to the sum of derivatives. So like if you take like the derivative of like, let's say, x squared plus sine of x, it's equal to taking the derivative of x squared plus the derivative of sine of x. And so what that means is that we can move this gradient inside of the summation, like this. Is that clear? Great. Okay. Okay, I'm going to go pretty quickly because we're a little short on time. But what we're going to do now is we're going to introduce a trick. This trick is just taking the gradient of the log. So what is the, let's say we have a function f of x. Then what is the derivative of the log? What is this? It's the derivative of f divided by f. By the chain rule, right? I mean, yeah, by the chain rule, because you take the derivative of the log, which is 1 over that value,
So you're treating it
times the derivative. Does that make sense?
as a natural log as well.
Yeah, it doesn't really matter. Yeah, we'll use the natural log in this case. Yeah, but you could use change of base if you wanted to. So that same logic applies to the gradient. The gradient of the log of p of tau is equal to the gradient of p of tau over p tau itself. That makes sense? And we can move this to the other side, and we get this term here matching what we have here. And so this is nothing but p of tau times the gradient of the log of p of tau theta times r t. Now, it's really important to focus on this part here. This is expected value. One thing we can do to simulate expected value is take what's called a Monte Carlo simulation. So there's a district in Monaco called Monte Carlo. There is a lot of gambling involved. And so a mathematician named John von Neumann in the 1940s named the Monte Carlo simulation method after Monte Carlo in Monaco, because you can use the Monte Carlo method to approximate the expected value of your winnings at a casino. So what that means is if you want to approximate an expected value, you can just take samples from the environment. So let's say like you have some scenario in which you're flipping a coin, or like you're rolling a dice, and you have a 1/6 chance of winning. But you don't know that you have a 1/6 chance of winning. You don't know how much you're winning. But in theory, the expected value is like, let's say, 1/6 of 6 plus 5/6 of -1. And we know that this expected value is positive. But let's say you don't know what the probabilities are. So what you do is you just roll the die as many times as you can, and you're going to observe the expected value. So this is the roll, and this is the value. So let's say the first roll you roll 2, and the next roll you roll 3, the next roll you roll 6, then 1, and then 1 again, and then 2. So what is the value? This is going to be a -1, -1, -1. This is going to be a 1, -1, -1, -1. So what's the expected value that we calculated? Well, we've had 6 trials, and the average value that we have is 1 minus 5 times 1, or this isn't 1, this is 6, because the winning we get is 6. 6 minus 5 is 1. This is our theoretical expected value, right? So by sampling from a distribution, we can approximate the theoretical expected value. It won't always match up like this perfectly in practice, but you'll get a very close result just by sampling. So if you run for many trials and average over the trials, average the value you get the expected value. Does that make sense? So using a Monte Carlo simulation, we can let this be 1 over n, where n is the number of samples. I equals 1, and n up here. And this eliminates the probability term, because we're sampling from the distribution, and that probability is inherent in the samples we get in the distribution. We get the gradient of the logs, p, tau, theta, r, t. And now we want to find out what the gradient of the log is. So recall from the Markov chain that the gradient of the log of the probability is going to be some expression of the gradient of the log of a multiple of events. So it's the probability of A going to B times the probability of B going to C, and so forth, based on this tau, this event sequence. And so what that means is that the probability of a given sequence tau and parameters is equal to a product starting from t equals 0 to time step t, termination time step t, of the probability of that individual state given the current state and the action times the policy of the action given the state. So all this means is that we multiply all the probabilities of the next state by also the policy, which is a little bit different from the Markov chain, because your agent is capable of taking actions. And so we have to multiply by the conditional probability of taking that action given that state. And so this chain will eventually get you to this sequence tau. So what's interesting here is that if we take the log of this, the log of a product is equal to the sum of logs. So this is actually equal to the sum starting from t equals 0 to t of p of state equals 1 given state t and action A plus the policy p pi theta of at given st And what's interesting if we take the gradient is that if you take a partial derivative with respect to a variable that's not contained within the function that you're taking the partial derivative of, you get 0. Because from the perspective of that partial derivative, it's a constant. And notice that in the probability distribution, there's no theta term, meaning that theta is not involved in this computation. And so this is a constant. And so if you take the gradient, then recall that this will go to 0. And this gradient we can push in to the sum. And so what that means is that this is nothing but the average over n trials, I equals 1, n, of the sum from time step t equals 0 to t of the gradient of the policy of the action given the state multiplied by, and we can expand this reward function to sum over all time steps starting from 0 to the r of that particular time state in action. And because we're taking this I ranging from 1 to n number of samples, we need to consider that the actions and states are going to be from that ith sample. And so this I here is not an exponentiation, it just means the ith sample. And so we've derived a complete gradient of our utility function purely in terms of the policy and the reward which we receive from the environment. Any questions on this? Yes.
Oh, the log.
Oh yes, you're
multiplying
absolutely right.
terms.
Yeah, so this is the gradient of the log. Good catch. Thanks. Any other questions? So this is policy gradients. And the problems it solves are continuous action spaces, and theoretically much better performance. Now, a problem with vanilla policy gradients, this method is called vanilla policy gradients because it doesn't introduce any other methods, is that it has a very high variance. So if you learn from statistics class about variance and standard deviation, what that means is that any sample that you take could influence the actions that you take significantly. So if you take a bad action, that will get you bad next states, which in turn will cause you to take even worse actions, which will get you into worse states, and so on, and you'll never collect good data, because you'll always be stuck in these bad states taking bad actions. So variance is a huge problem in reinforcement learning. And policy gradients, as they're formulated in this manner, have a very, very high variance. And this is really detrimental to the performance of the model in general. So we want to minimize this randomness. And a couple of ways we can do that are to subtract a baseline from this reward function. So if you take the variance of a distribution with smaller values, it will be lower than the variance of a distribution with higher values, just by the nature of variance as being the average, the expected value of a random variable x subtracted by the expected value of that squared. So we won't go into the derivation of variance too much, but essentially, as this is formulated currently, it won't work very well in general. It might get lucky and work very well, but oftentimes random noise, bad states and bad actions will cause it to perform really poorly. But there are a couple methods we can use to improve upon that, such as subtracting a baseline. We don't have time to cover them right now, so I'll just move on really quickly to the next method. Yeah, sure, which is trust region policy optimization. Since we're also running short on time, I won't work through the derivation of this either. But essentially, we're going to constrain this utility function update to a trust region, which means that we want to optimize a function within this bound. This bound, what we call the trust region, instead of the entire function. And this makes it a lot simpler to work. And so this is an example of trust region policy optimization running on literally figure running. And it learns to run on the simulation.
Recommendations getting exposed right now.
That was an alternative method versus trust region policy optimization. Trust region policy optimization, which performs much better, or TRPO as we consider it. And the way we compute this trust region is we take this thing called the KL divergence, which compares two probability distributions. Since we don't have time, I won't cover this, but you can read about this on Wikipedia, or you will learn about this in your statistics courses. We can probably move on to proximal policy optimization. Yeah. Proximal policy optimization is a first-order approximation of trust region policy optimization. So it turns out it's actually very hard to solve constraint optimization problems. If you're taking Calculus 3, you know about Lagrange multipliers as an example of a constraint optimization problem. If you're trying to optimize a function f of some number of variables, where another function g is bound to a constraint, like let's say g of x equals 0, and finding the optimal values of x along some contour, this is like a problem that you can solve with Lagrange multipliers. But in general, constraint optimization problems are very difficult to solve. And so proximal policy optimization removes this constraint optimization constraint by subtracting the KL divergence of the utility function that we define for TRPO, and maximizing that instead. And so this is proximal policy optimization. You can see it's operating in a much harder environment because in the running example, it's only running along two dimensions, or really, yeah, 2 dimensions. It can move like its joints up and to the right. But here, it can move in 3 dimensions, which is much harder. This is much more like a realistic environment in which it can move in. You can see it starts to run over many, many episodes. Yeah, and
100,000.
Yeah, over 100,000 episodes. So yeah, we can move on to the final video, which is this is OpenAI 5, which is a model that plays Delta 2 over a large number of time steps. Yeah, turn the volume way up.
Okay, hold on. I think I can.
Yeah, we can full screen and probably skip a few.
Okay.
Yeah, so these are human international champions at the game Delta 2, which is one of the most competitive video games. You compete in a team of 5 against another team of 5. You have to coordinate in order to defeat your opponent.
Looking to dive in deep past the tower with this gyrocopter and Sven combination. They've got the voodoo restoration though, OG. No tail, keeping the 2 of them alive as OG's able to turn, bring down the Sven. Still though, trying for this SF. Gyro desperate for the kill, but he cannot find it. As with the Fisher and the heals from No Tail.
Picking up the Witch Doctor, we've seen how the harassment, OpenAI is super good about being able to do that, and the voodoo restoration is cutting a lot of that out and making these fights go their way.
And we're going to see the AI going, this time with the help of the CM. They're looking to lead in onto the SF. No Tail's there though, again, as you mentioned, this voodoo restoration just making it that little too hard for the AI to instantly kill the SF. They'll get another stun out. He's still alive though. Finally, they get that kill onto Anna.
So you can see here the OpenAI second bot.
Trying to see if they can find even more potentially the OpenAI as it looks towards No Tail with the rocket barrage. The gyrocopter finds another. This time, the OpenAI is getting away with the aggression up top. They realized it wasn't working with just the Sven and the gyro, so they added that crystal maiden and it makes all the difference.
That's okay.
From experience, we thought the
like here?
Skipped right before that, a little bit before that, a little bit before that.
They know the
more. Yeah, just like right there.
From the Sven, a snipe from the sniper. As Anna will try and do something.
Has anybody here played Dota 2?
BKB, the first ult comes out.
No.
Killing off the Sven.
It's a hard game, let alone a bot playing it.
Still though, they have to be careful of this sniper as it's doing so much damage towards the SF. Anna will fall. No Tail TP's in, he's got the death ward, but the physical damage from the sniper pulls apart the Witch Doctor. They are trying to keep them drawn away from the Ancient as both Thompson and Jerax are trying to take OpenAI's focus away from ending the game. Jump forward, Tensor, but it doesn't matter. The creeps are on the Ancient. GG is called, and OpenAI take game 1 and cap.
Yeah, so I guess we can.
Pretty terrifying. It was close at the start, but one thing
Yeah, so the AI won the championship against human international players. This is a very advanced video game with a lot of moving parts, many different mechanics. Actually, a lot of Dota 2 players now train by playing against bots that use reinforcement learning. Yeah, it's also like in the game of Go. Now a lot of students who learn Go competitively are learning from AlphaGo, and rather than humans because it performs so much better. So yeah, this is the.
It's been running for a little bit.
Yeah. One thing that happens with Q learning, sometimes it crashes a little bit. There's a lot of variance, as you saw in those graphs, where spikes would go up and down as far as the rewards would, cumulative reward would go.
Yeah.
So yeah, that concludes our advanced reinforcement learning series. Hope you enjoyed. Hope you learned a lot about how we formulate reinforcement learning problems, how we formulate environments, utility functions in order to maximize reward, and all the concerns that we have and considerations in solving these problems.
That's it.
So,
Yeah.